Start. So this week, this week we're gonna talk about new concept, which is online algorithm. Okay. So in one sentence, this is online algorithm is a way, it's an algorithm to make decision for future, make good decision for future without knowing the future. Okay. So, by the way, the slides today, it's my attempt to use ChatGPT to create it, but not that good. Yeah, I need to edit it quite a lot, but yeah. So that's why it's in LaTeX. Yeah. But anyway, okay, so let's start. So first thing about online algorithm is the concept of competitive analysis. Okay. So let me kind of gently introduce you the setting. Okay. The setting of online algorithm is that you will have input that is given to you sequentially. Think like you wake up one day, you need to decide something. The next day come, you need to decide something. So the input is what you see in each day, and it comes to you sequentially. Okay. And what you need to do is you need to make this decision based on the information that you have so far. And the future is unknown. You don't know what will happen. Okay, so we don't know the future. Okay, and so this is the key, the theme. You have sequential input, you make decision, and your decision cannot be revoked. And you need to do something with this limited knowledge. So how do you do this? And how do we even talk about what is a good decision in this setting? Okay, and to formalize what is good decision in this setting, we use a framework called competitive analysis. Okay, so what we do is basically try to compare the decision or the solution that we have with the optimal offline algorithm. What do I mean by optimal offline algorithm? It's an algorithm that it assumes that it knows everything, including the future. Okay, it sees the future, everything, and in each day it makes some decision, and you compare your solution to that guy, the oracle guy. Okay, and then we try to compare it to this offline algorithm and say that even in the worst case, our solution is not as bad. It's not too bad compared to the oracle guy. Okay, and the ratio between our solution and the oracle guy is called competitive ratio. So let's be precise. So let's say that let I be the input sequence. Okay, it can be any kind of sequence, and then let's say that C online I is just the cost of your online algorithm that don't know the future. Once you finish the sequence, then you see how good is your solution. This is the cost of your solution. And C offline I is the cost of the optimal offline algorithm. And so you just compare the ratio between these two. Okay. And if this ratio is always small for any input sequence, then that's when your competitive ratio is small. Okay. So you see, this is just so similar to notion of approximation ratio, right? For approximation ratio, you have this is an optimal cost, and this is your cost this is the cost of your algorithm when your algorithm have a limited time, let's say polynomial time, and you compare it together. Yeah, the restriction of the algorithm is in the different way. Is the restriction of your algorithm is that you don't know the future. Okay. Okay. So that's so it's just kind of really similar concept, but in different aspect. Okay. And so competitive ratio will be small if if competitive ratio is small, then it means that you have better worst case performance. And in the ideal case, it should be close to 1, but sometimes it might be impossible to get competitive ratio to be 1. So I hope you kind of get the theme. So far, what we have learned in class is offline algorithm. You have the whole input, you have complete knowledge of everything, and you just try to solve some problem and try to get optimal solution. And for online, yeah, you have limited knowledge. You have to make decision incrementally, and you might not get optimal solution, but you want it to be competitive to the optimal one. Okay, so let's see some example. The most simple one is this problem called ski rental. Anyone have seen this problem before? Cool. Okay, you have seen it. Okay. Anyway, so in this problem, right? Imagine that you have vacation and you go to a ski resort or something. And then on each day, you need to decide whether you want to buy or rent the ski. If you want to rent a ski, you need to pay $1 per day. So if you rent on every day, you need to pay quite a lot. Or on some day, you can also decide to buy the ski. Let's say the cost of buying is capital B. But if you buy it, you might need to pay a lot, but from now you don't need to, the next day you don't ever need to pay. Okay. And the situation is that, okay, you go to a ski resort and you just don't know when your boss gonna call you to come back from the vacation. Okay, so you just don't know number of the ski days. Okay. But so if it turns out that, okay, somehow your boss gonna just call you back after 1 day, you better just rent for the first day. But if it turns out that your boss never call you back for the whole life, maybe you just buy and you have a good life. And so yeah, so that's the situation, and this kind of capture a lot of real life application. You need to decide whether you want to pay a bit but continually, or you want to pay a lot but just once. Okay. So the problem is clear? Okay. So let me ask you. Suppose that you know exactly when your boss is gonna call you. Let's say the boss will call you on day T. You have T days. If you know this, what should you do? Yeah.
If B is less than T, you should buy, else you should rent.
If B is less than T, then you should buy. Exactly. Otherwise, you just rent. So it's quite simple. So yeah, if T is at least B, just buy the ski, because otherwise you will pay more than B. And if T is strictly less than B, just rent. You will need to pay less than B. And so the optimal cost is just going to be the minimum between T, the number of days, the number of time step, and B. That's the optimal cost. Optimal offline cost. Okay, now you don't know when your boss is going to call you back. Okay. So I want you to spend maybe a few minutes to try to think what you want to do. How do you make sure that you don't pay much more than this thing? So I give you 3 minutes or something. Okay, so anyone have some suggestion what you want to do? Okay.
Maybe you can rank for the first B days, and then after B days, if you're still not called back, then you just buy those keys. That way, I think you get ratio of 2.
Exactly. Exactly. Good. So what Andy just said is this. We just say that, okay, just rent the ski for the first, let's say B minus 1 day. And if you still not need to go back, then on the B day, you just buy the ski. Okay. And now I claim that your competitive ratio is going to be 2, meaning that you never need to pay more than like your cost. Your cost is at most 2 times like offline cost, which is mean of T and B. Right? Okay, so it's not hard to analyze this. Just need to make 2 cases. So let T be the total number of ski days. If T is at least B, then what is going to be your cost? Well, you're going to rent for the first B minus 1 day, and then you pay for buying after that. So your cost is 2B minus 1. The optimal cost is B, because we know this. So the ratio is then like something that is less than 2. Okay. And how about when T is strictly less than B? In this case, both optimal algorithm and our online algorithm will just rent for T days. So the ratio here is just really 1, which is better than 2. So in any case, the competitive ratio is at most 2. So that's like very simple deterministic online algorithm. And you can guarantee that you are never worse than like the offline one by a factor of 2. Okay. Now, let's talk about randomized algorithm. Okay. You can actually do better with randomization. Okay, but first of all, I need to like formalize the model when we talk about randomized algorithm for online algorithm. So, to talk about online this, we need the notion of adversary, and we will in particular look at the notion of oblivious adversary. Okay. So adversary is just like in the context of online algorithm, it's just a guy that generates the input sequence that you don't know. So in the context of ski rental, so your boss is your adversary, right? It's just generate this input sequence that you don't know. Yeah. Like on each day, whether like you can stay or you need to go back. That's the input sequence. And now, for oblivious adversary, is a type of adversary that doesn't see the output of the online algorithm. Okay, so it's just oblivious to the output. Okay, but I will still assume that it knows the source code of the algorithm. Like it knows the procedure, but if your algorithm is randomized, say, then it doesn't know that the coin that you tossed. It doesn't know the result of your coin tossed. In particular, it doesn't know the output, the randomized output of your algorithm. Okay. So that's that's the notion of oblivious adversary. Okay. So, and in this class, like, and mostly for online algorithm, people will assume that if your algorithm is randomized, then you assume that the adversary is oblivious. Okay. And if that is the case, then the random choice made by the online algorithm will be independent from the input sequence, right? Because the input sequence is just oblivious from the output, and from the it's just oblivious from you can think like this. You can think like the input sequence is just fixed from the beginning, and it's just revealed to you one by one, regardless of the output of your algorithm. So in other words, input sequence is fixed from the beginning. And it's just revealed to you one by one. Okay. And you see, like, the performance of randomized algorithm, like, it might depend on this assumption whether this adversary is oblivious or not. Because if the algorithm is oblivious, if the adversary is oblivious, then it might try to look into your output and try to generate the next input sequence that kind of hurt you. But now we will assume that the adversary doesn't really see anything from the output. So in some sense, the extent that the adversary can generate bad input for you is less. Make sense? Now, importantly, for deterministic algorithm, it doesn't matter whether the adversary is oblivious or not, right? Because the adversary knows the source code of the algorithm, so it knows exactly how deterministic algorithm will behave. There's nothing that the adversary can learn from the output, because there's no random choice anyway. So for deterministic algorithm, it just doesn't matter whether this adversary is oblivious or not. But for randomized algorithm, if the adversary is oblivious, then maybe you can guarantee stronger competitive ratio. So yeah, question about this concept. Okay. And the reason why we assume oblivious adversary is that it's known in literature that if your randomized algorithm doesn't assume oblivious adversary, then it will be you cannot really exploit randomization in this context. The competitive ratio can be as bad as deterministic algorithm. But this is kind of out of the scope. But if you want to look into this, why this is the case, that's the paper. Okay. Now, what we're going to do is just the competitive ratio of randomized algorithm is just we look at the expected cost, And then for the competitive ratio, we just compare the expected cost of your online algorithm with the offline solution. Okay. The expectation is taken over random choice. And you see like this sequence I is just independent from R, from the random choice. And that is true only because the adversary is oblivious. Okay. So let's see, like in action, how do you exploit randomization? Okay. So what I'm going to show is that with randomization, for this simple ski rental problem, can actually get better than 2. But for deterministic, then 2 is the best possible ratio. So randomization is more powerful, like give you more power. Okay. So let's consider this. Okay. It's a simple randomized algorithm that, okay, in the beginning of day 0, you just toss the coin and see if it's head or tail. If it's head, then just do the first algorithm that we have seen, rent for b or b-1 days, let's say b days, and then buy after that. That's the algorithm, just the same algorithm before. But if your toy, like if the coin that you toss is give you tail, then you instead just rent for this many days, 3, 4 B days, and then buy. Okay. So that's the algorithm. And now, just from simple calculation, we will see that this is better than 2. So let's see. So, okay. Suppose that t is the number of days again, right? If t is less than 3/4 b, then you know that your cost is t. This is actually deterministic. Like your cost, you're gonna rent for t days, and which is the same as optimal cost. So in this case, you are as good as the optimal solution. So what about when t is still at most b, but now greater than 3/4 b? Okay. In this case, you have the expected cost like this. If for 1/2 probability, you will just rent for the first b day, right? So with 1/2 probability, you will just pay t. But another half probability, what you will do, you will rent for this 3/4 b days, and after that you buy. So that's your expected cost. But now let's try to analyze how is this compared to opt. Okay. So, by the way, in this case, you know that like t is opt, right? In this case. So t is opt, so this part you can relate to opt. How about b? You need to relate b to opt somehow, but you know that b is at most 4/3 t. So this is like at most 4/3 opt. So now you can calculate. So this is opt, and the b here is 4/3 opt. So you just calculate and sum them up, so you get you get 1/3, one half here, and 1/2. This part is from this thing, and 4/3 opt from B. Just simple calculation, but once you sum them up, you get some number. And this number is better than 2, smaller than 2 opt. Okay. Similarly, what about, what if T is greater than B? In this case, you know that B is opt, right? And what's the expected cost? Well, with probability 1/2, you rent for B days and then buy. Another 1/2, you rent for 3/4 B day and buy. So that's like 15/8B. And B is opt, so this is 15/8 opt. So in any case at all, you never pay more than 15/8 opt. So the like compare this coefficient, this coefficient, and this coefficient of 1. This is always at most 15/8. So you get better than 2. Okay, so you see, like let's try to understand what's going on, right? Like how is super simple algorithm like this can give you something better than 2. Anyone, do you have like an intuitive understanding? Like ignore the calculation. You get better than 2. How come what did we like? How come we get better than 2? There's no right answer here. It's just your like intuitive understanding. Any? Yeah.
I guess because you compute the competitive ratio with like the expectation, like in the worst case, it will still be 2. Like if you don't have the probability, like the uncertainty, like there is still half probability you will get like competitive ratio is 2. But there are another half probability you will get better result because you buy it early.
Yeah. So in the worst case, yeah, we still like in the worst case overall randomization, you might need to pay 2, but somehow by averaging over this random case, it's better than 2. And yeah, so at least my take for like intuitive reasoning, how come this happened, is that, okay, it's better than deterministic. And the reason behind it is that the adversary cannot really predict your buying date. The adversary cannot predict whether you're gonna buy on day B or 3/4 B. And because of that, once like you will see soon that if the adversary can predict exactly when you will buy, your cost is going to be as bad as 2, like 2. Your ratio is going to be 2. But here, like they just like the adversary just don't know when you're going to buy, and even if you buy at day 3/4 B, they don't see it too. So because it's oblivious. Okay. Yeah.
Is this the lowest competitive ratio for the ski rental problem, or is there like a lower one, lower than 1.75?
This is lower for the ski rental, but in general, you can use randomization to get better competitive ratio for any problem. And this is basically the reason behind all improvement using randomization. So let's see, like, if the adversary can predict the buying date, why you need to pay, okay? So this is really the limitation of deterministic algorithm. Okay. So let's see. In contrast, right? If your algorithm is deterministic, then I claim that the adversary can predict the buying date. When your algorithm is deterministic, the adversary must know when you will buy. Why? Because suppose that K, if let's say that your algorithm decide to buy on day K, you know that K here just solely depends on B, because B is really the only parameter of the problem. Okay. And K cannot depend on anything else. There is no random choice. K just depends on B. Okay, so K is a function of B. But the adversary knows the source code and the input, so it must know F, the source code of the algorithm, and B, which is the input. So the adversary can predict what K is if your algorithm is deterministic. But if the adversary know what K is, then how would it do? What would it do to make you pay the most? It would just say that, okay, set the last day to be K, right? Like think like, okay, you just bought this ski, right? Just then let's end this vacation. That's the strategy of the adversary. So this is the this can be the strategy of the adversary, and in this case, right, the competitive ratio will be what? Will be like the cost that you pay is gonna be K minus 1 plus B. One sec. Yeah, K minus 1 plus B because you rent for this many days and then you buy. But you know that the optimal cost is minimum between K and B. And this ratio is at least 2 minus 1 over B. Like you can use calculus or something, but yeah, it's this is at least 2 minus 1 over B. And you think like this is like basically can be, so this is basically 2 because this thing can be arbitrarily big. Like this thing just go to 0 when B is big. Okay. And you see this argument doesn't really work if the adversary is oblivious, because you don't know for sure when what is K. If the algorithm is randomized and the adversary is oblivious, then first of all, this K here is now some random number, right? And the adversary is oblivious, so it just cannot observe what is the day that you buy, and then say that the last day is the day that you buy. It cannot do this. So you see, that's why our randomized algorithm can go below 2, strictly below 2. And the deterministic algorithm will need to pay 2. Make sense? Okay. So the state of the art of this problem is basically solved. This problem is solved. For deterministic, you just saw the best algorithm is the two competitive, and you just saw how to use randomized to go below 2. So that's like better than 2. And in the next class, you will see like this one is quite ad hoc, right? It's just some simple algorithm. Next class, you will see like a principal way to design like randomized algorithm that is actually optimal. It turns out that the ratio is something weird, like e over e minus 1, and this is optimal. So next class you will see this. So it's going to be based on the notion of this method, the primal dual thing that we have seen. We're going to make it work in the online setting. Okay. So that's ski rental. Let's see another simple problem that is fundamental in the online setting. It's called online scheduling. So imagine that the situation is this. You just want to distribute the online sequence of jobs into M machine. Imagine like this. You have, let's say, 3 machines. And then there is a job given to you online. The first job the first job might be like this. So the length here is like the amount of time you need to do to finish the job. Okay? And you just need to decide whether to put it into which machine. So let's say that you put job 1 of size P1 to this machine. Then the next job comes, maybe it's of size P2. Then you just decide whether what you want to do, maybe here. So this is P2. And then the next job comes, maybe you put it into this is P3. Then the next job comes. And you decide where to put, and so on. Okay. And the goal is really just at the end, you get a bunch of you get a bunch of jobs on each machine, and you want to minimize the maximum load. So you want to minimize this thing, the maximum load over our machine. You want this to be small. But yeah, you don't know the number of jobs that will come to you. It might be many. And for each job, you also don't know anything about its size until it is reviewed. So that's the problem. And you can again imagine that this is, you can use this in many like computation, like distributed workload of web servers and so on. Okay. So yeah, there is a very simple heuristic that is to be greedy, right? So what you can do, like maybe the first guess really is to just assign each task to the least loaded machine. That's the very simple algorithm that we might think of, and so sure it's simple and efficient to implement. So now, okay, it makes sense. How do we analyze it? That's the question. Okay. So let's try to analyze it together. Okay. So I claim that this algorithm gives you 2 competitive ratio. I want to give you some time to think actually. So let me define two things, maybe four things. Suppose that, let's say that L opt is the optimal max load. And L greedy is the max load of greedy. So what we wanted to say is that L greedy is at most 2 L opt for all input sequence. This is what we want to show. Okay. That's the goal. Now, let's see. Now, I want to define one thing. Let's consider two things. Let A be the average load. So A is just this thing. A sum over all J from 1 to n Pj. This is over M. This is average load. So you see, like, the total load, this is just the total load of all jobs, right? Like, let's say there are n many jobs. This load need to come to some, like, all of this load will need to come to some machine. So total load is this sum, and then I just average over M. So I know that if I have this many jobs like this, the average load need to be like this thing over M. Okay. Can you tell me the relationship between L opt and A?
Cannot be lower than A, right?
Exactly. So L opt must be at least A. Because the average load is no matter how you schedule, A is average load, and L opt is like the max load. So L opt is at least A. Let me define this thing too. P is just the maximum job. Is max job. Okay. So you now know too that this guy must be at least P2, right? Just because this max, the largest job need to be assigned to some machine. So no matter what, this must be like so the maximum load must be at least this P. Okay, now I want you to think, can you bound L greedy in terms of A and P? Something like A and P. So Yeah, let's just do it together, right? So I claim that the load of greedy is actually going to be at most A plus P. That is not super clear, but if it is the case, then you know that this is now at most 2 L opt, and you're done. So we need to prove this. Okay. So let's prove it together. This slide is not so good, but yeah. Let's see why this is the case. This is just what I wrote before. So we just need to see why L greedy is at most A plus P. So let's just look at the scheduling of greedy. This 1, 2, 3. And okay, you might have a bunch of load. Okay, maybe like this. So like this might be the first job, second job, third job, and like this might be like the fourth one. I don't know. And then there might be. So this is the fourth one. No, this should be the fourth one, and this should be and then the fifth one maybe here, and then the sixth one, yeah, 7, 8 something. So you might get like you keep doing greedy. Okay. Now what I want to look at is the job that finished last. So there can be like many jobs. Which job finished last in this diagram is a sixth one. It might not be the job that come last, but it finished the last. Okay, so that's my L is 6. So now let me define T to be the starting time of this T. It's just the starting time of the job L. So now you know that greedy, the load of greedy is just T plus L, just from the definition how we define it. Okay. And the goal is that I want to say that T is at most A and PL is at most P, and we would be done. So let's do that. So at the time, you see, at the time that at time T, yeah, you know that all machines have load at least T. Because we are greedy. Otherwise, we wouldn't even put 6 here. We are greedy. So all machines have load at least T. So you know that if you sum the load of everything before the 6th guy, before L, sum the load over all J when J is strictly less than L. This must be already more than MT. But it means what? It means that T is at most a sum. Let me just write it down. J is strictly than L, which is at most sum of everything, even until to N. And that is A. So T is at most A. So greedy, the load of greedy is at most A plus PL. PL is at most P because P is, the max load, the max job. So that's why L greedy is at most A plus P. Because L of greedy is at most A plus P, but L opt is more than at least A and P. So you get that greedy is at most 2 times L opt. Questions? Okay. Good. So now, so I claim that you can actually get better than 2 just by a bit. You can actually get something like 2 minus 1 over m. Okay. And the idea is simple, like just the same algorithm, but just refine the analysis a bit. So you see, when I try to bound this thing, like there is some like relax. This is quite crude here, right? To set a t is at most A. Here I just sum over all jobs strictly less than L. But and then this is I sum over all jobs here. So I miss at least one job for sure, because I don't include PL here. Okay, so that's with this you can refine a bit. Let's see how. So instead of you have this thing when L is strictly less, J is strictly less than L. So let me write down differently. T is now at most this sum J at most L minus PL over A over M. Okay. So this term is at most A, right? So this is basically at most A minus PL over M. Okay. So it means that, well, you get that L of greedy is at most A minus PL over M plus PL. So it's A plus 1 minus 1 over M times PL. And thus you get P here. So yeah, now I just from here, both A and P is at most L opt. So we get that this is at most 2 minus 1 over M instead. So not that interesting, but just shape it a bit. And this is good when M is small, right? When there are 2 jobs, now you get better than 2. When M is 2, this is now 1.5. So quite better than 2. Okay. How good is this? So I claim that our analysis is actually tight. And the example is just simple. Imagine that you have M times M minus 1 jobs of size 1. And then at the end, you get 1 job of size M, right? Then what greedy will do, will just balance the job of size 1 here. And then at the end, you have no choice but to put this big job at the end somewhere. But so this is gonna be of size M minus 1, and this is of size M, and then this is of size M here. So the total length here is 2M minus 1. But you know that the optimal solution, you can just arrange it like this. So the optimal solution here is going to be M. This is M. So the competitive ratio is 2 minus 1 over M. So there is some instance such that greedy is worse than optimal solution by 2 minus 1 over M factor. And for every instance, greedy is not worse. Like for every instance, the competitive ratio is at most 2 minus 1 over M. So this is tight. Nothing you can improve for greedy, so we completely understand it. But there are better algorithms than greedy, actually. Okay. And I will tell you the state of the art soon. But okay, what we get from this slide is just the lower bound for one algorithm, just for greedy. Can I want to argue that you can try to come up with some lower bound that works for any algorithm too. Okay. Similar to what we did before, we come up with the way to lower bound any deterministic algorithm for ski rental. Right? We want to do something similar. So let's try to do the lower, let's try to see how to get lower bound for any deterministic algorithm, not just greedy. Okay. So let's get the algorithm lower bound for any deterministic algorithm. So suppose that there are two machines. And so there are two machines. And then the adversary just first generate a sequence of two jobs, each of size 1. Okay. And if the algorithm somehow put the job into the same machine, then we just stop. The adversary just stop, and now it claims that okay, now the competitive ratio is 2 because op is obviously 1, but you pay load of 2. If instead the algorithm decide to distribute two jobs into two machines like this, then what I will do is that the adversary will generate the third job of size 2. Just put another job of size 2 here. So this is first two jobs. If they distribute like this, let's generate the next job of size 2. It must be put somewhere, so let's say put here. Okay. And in this case too, you see that this is load now is 3, but the optimal load is 2. So in this case, the competitive ratio is at least 3/2. So no matter what the algorithm decide to do, right? Whether after the first two jobs, whether the algorithm decide to put the two guys on the same machine or distribute them, we as an adversary can generate the bad input to the algorithm so that it do worse than optimal solution by at least a factor of 1.5. Okay. So if you can come up with the strategy for adversary so that the algorithm will do always a worse than optimal solution, then you get a lower bound. Okay. Make sense? Like why did we get 1.5 lower bound? And now I claim that this lower bound will work only for deterministic algorithm. So that's the quiz for you. Why is that? Why this lower bound doesn't work for randomized algorithm that assume oblivious adversary?
Just from looking at the source code, the adversary can't, like, in this case, he can determine where exactly the algorithm is going to put the next job. But with randomization, like, it could put the 1 in machine 1 again, and then put the 2 in machine 2 and actually get an optimal.
I'm not sure can you describe your
Yeah, like, you just can't determine, the adversary can't determine precisely where you will put a job.
Yeah, if the algorithm is randomized, right?
Yeah.
It cannot decide, like it doesn't know for sure whether the algorithm will put the first 2 jobs at the same machine or distribute them. That we don't know for sure if the algorithm is randomized. And adversary is oblivious, then we don't know this. So another way to look at it is that this strategy for adversary is obviously adaptive. Like it tries to see what the algorithm does and adaptively generate some bad input for the algorithm. Right? So if your algorithm, if the bad adversary is adaptive, then that argument will not work against randomized algorithm that assume oblivious adversary. Because your adversary is not oblivious, it's adaptive. Okay. Good. So now let me tell you a bit about the state of the art. So this greedy algorithm is known like from the ancient time. Like how long is that? I don't know. almost 60 years ago. And but it turns out that quite a long time ago too, 30 years ago, people actually know how to beat to competitiveness strictly. Like get something like 1.9. And the best known right now is 1.92. Some weird numbers. How about lower bound? What we show today is 1.5, but only works for deterministic algorithm. But the best known is actually better than 1.5, and it also work with a randomized algorithm too. But you see there is still this gap, and the state of the art is this, really. So this is a performance for this is M, the number of machine, and it can start from 2 to infinite to like any numbers. And this is what we see today, the greedy one. Greedy will have competitive ratio of 2 minus 1 over M. So it goes to just 2 when M is big. But yeah, there is a deterministic algorithm that actually is strictly better than greedy when M is big enough, like 1.9 something. And there is a lower bound of 1.8 something for deterministic algorithm. So even for deterministic algorithm, there is some gap. Like we don't fully understand this super simple problem yet. And for randomized algorithm, when M is 2, like there is an algorithm that gives you 8 over 4 over 3 competitive, and that's tight. But now if the number of machine is more and more, then the low bound and upper bound is not tight. And when m is big, actually the best algorithm is just deterministic. So yeah. So I just kind of I just find it quite interesting that okay, like this super simple problem is we don't understand it yet. And yeah, would be cool if to close this gap. And if you want to learn more about it, you can go to this survey. Okay. So actually, I don't have much to say now. Like, let me tell you what I'm gonna do on next class. Next class, so what we have learned is what we have learned about LP is that we have learned about LP routing. And also primordial method. We use these two techniques to get approximation algorithm in the offline setting. Okay. We will try to make this thing work next time, both of them, in the online setting. And so you will see how like using LP, there is a principal way to come up with online algorithm. So today is kind of ad hoc, like us do some heuristic, some greedy. Tomorrow is gonna be like the next 2 days gonna be more principal way to design online algorithm. Okay, so yeah, we finished today. Yeah, that's it.